one of the reasons I fell in love with chemistry was that it explained the world around me. So I could look up and be amazed at a fireworks display. But I could also look up and see barium, or magnesium, or sodium, or even strontium in the brilliant reds. You see, chemistry didn't take away the wonder of these kinds of things. It enhanced it, because truth is always stranger than fiction. Because we now know that these colors are ultimately caused by electrons changing their orbitals, getting excited and relaxing back down and emitting photons. And that's amazing. And it's all ultimately related to electron configurations. So virtually all of the chemistry that we observe on a day-to-day basis has to do with electrons around atoms. And virtually all of what electrons are doing and how they're structured around atoms ultimately has to do with orbitals, and more specifically, electron configurations that we talked about last class. So this is really a fundamental concept to help us understand how electrons are distributed around atoms. So let's just take another look and maybe expand on the concept of electron configurations just a bit today. So for example, take the sulfur atom. Sulfur is atom 16 in the periodic table. That means it's got, of course, 16 protons in the nucleus. If I wanted to write the electron configuration for sulfur, first of all, let's assume that it's a neutral sulfur atom, and therefore I would have 16 electrons to allocate in my diagram here. So doing that and using the Aufbau principle from a previous class, we know that we simply fill the electrons in the orbitals from the bottom to the top. And when we get to degenerate sets of orbitals, like the p's or the d's, we fill singly before pairing, and we tend to lean towards the high spin state if we can. So in this particular case, I've got 16 electrons, so I'll start with 2 in the 1s, and then I'll put 2 more in the 2s, that's just above it, and then we'll eventually end up putting 6 in the set of 2p orbitals. So that's a total of 10 so far if you're keeping track, and we've got 6 more. So I'll put 2 in the 3s, and now I've got 4 more electrons to place. So I can do this, 1, 2, 3, and now that 4th one can go there, and we can recall that really that 4th one could have gone in any of these because they would have all been energetically equivalent. So if I want to write the electron configuration for sulfur, or what's also known as the full electron configuration for sulfur, it's really just a listing of where all my electrons are. So in this particular case, I've got 2 electrons in the 1s set of orbitals, or orbital. I've got 2 electrons in the 2s orbital. I've got 6 electrons in the 2p set of orbitals. And I've got another 2 in the 3s, and then finally my last 4 electrons are in the 3p orbital. Now that's all well and good, and we could probably do this ad nauseum for any or most of the elements in the periodic table. But some students often worry a little bit about the fact that my orbitals here tend to overlap, right? So we've got a 4s orbital directly after the 3p orbital, and we've gone into a lot of detail about why that is, but it may not be intuitively obvious for a lot of students that that happens to be exactly where that overlap happens. And some students get a little bit nervous about, am I going to get the right order? Can I remember that after the 3p comes the 4s and then the 3d and so on and so forth? And one of the ways I want to alleviate that anxiety for you is to, perhaps draw a connection to the periodic table with all of these orbitals in a way that you may not have quite noticed yet. Now, if you're following along in the notes, of course I do write about this, but there's I think a fairly amazing coincidence, or it shouldn't be a coincidence, this is actually a consequence, would be a better word, of this orbital structure. And that is the structure of the periodic table itself. So if we take a look at a comparison, on the left, we see the orbital energy level diagram, as I've been using for the last couple of lectures. And on the right is a schematic of the periodic table where certain blocks in that periodic table have been highlighted in consistent ways. And the key here is to realize that the actual structure of the periodic table, how it actually is presented, is a direct consequence of the orbital model of matter. It is the quantum mechanical model of all of these orbitals, including their somewhat unintuitive overlaps like the 4s and 3d, that actually produces this table. And so maybe let me draw that a little bit more clearer in case you can't see it quite yet. So if you think about something like, for example, the hydrogen atom, super simple system, the last electron, and I guess the first electron, coincidentally, of hydrogen is just a 1s1, right? One electron in the 1s. And notice where hydrogen is on the periodic table, okay? Now, what about helium? So helium would be the next element in the periodic table, and it would have an additional element. Again, let's just think about neutral elements for the time being. And so helium's electron configuration would be 1s2. And again, if we notice where helium is in the periodic table, it may look as though my little 1s block over here is misplaced, but notice the gap right here. And in fact, there are some periodic tables that choose to put helium in this particular position. But suffice to say, I think we can begin to see the pattern where the orbital structure of these elements can correlate to where they are in the periodic table. Let's keep going. Just past helium, of course, we'd have lithium. And lithium, if we look at our orbital diagram, lithium would have another electron in the 2s. And according to the structure of the periodic table, lithium starts the next row. And so it'd be right here, directly underneath the hydrogen atom. Well, that's interesting because, as Mendeleev would have discovered many, many, many years ago when the periodic table was first being constructed or even conceived of, what was done was we would investigate the properties of the various elements, all kinds of things that could be measured at the time, things like, was it combustible? Did it, react in air? All kinds of, relatively qualitative types of measurements were made. And elements that behaved the same way were simply listed in a column like that, right? So if you found that hydrogen and lithium, behaved chemically very similarly, they would have been listed in a column together, in a family, right, or a group. And to this day, this is how we structure the periodic table. But if we connect this idea to the orbital model over here, we see that hydrogen was a 1s1 electron configuration. And now lithium is a 2s1 electron configuration. In other words, we can imagine that the electron or electrons around those atoms had a very similar distribution. They had a single electron distributed in an s-type orbital. And as elements, fly through the universe, their reactivity, as I said before, is almost always governed by their electronic structure. And so as one element comes into contact with another element, what will happen there is usually dictated by electronic structure. And so if you have a particular element whose outermost electron is just a single electron in an s-type orbital, or spherically distributed around that nucleus, you would expect it to behave in a very similar way to any other element that also had only one electron distributed in an s-type orbital, which is the case for both lithium and for hydrogen. Now, of course, we would expect to find another element eventually with just one electron in an s state, but let's just wait a second and see what we get before we get there. The next element, of course, is beryllium. So beryllium would have a 2s2 configuration, and notice that the the width, if you will, of the periodic table here, this leftmost block, if you consider it that way, or if you look at it like that way, is 2 elements wide. And it's 2 elements wide because there are 2 electrons in this 2s state, right? You have one whose valence or whose last electron would be the s1, and then the second one who would be the s2, and that's, again, beryllium in this case. Continue on, notice we have what you might have thought was this giant gap here, this vacancy, this place where there are no elements, and maybe we thought there might have been. However, if we continue, we would get to, of course, boron, and boron would be an element with a single electron in the 2p set of orbitals. And notice over here, we've got 6 elements, 1, 2, 3, 4, 5, 6, all the way over to fluorine, right? 6 elements there. And notice also that there are 6 possibilities for electrons to be placed in the 2p set of orbitals. So as I walk through this particular set, and I go from boron to carbon to nitrogen, so on and so forth, I will match the electron configuration over here on the left with my position on the periodic table. Now, once I fill all that up, I've got all my orbitals filled up, I'm way over here at neon, the farthest over to the right. I think I might have said fluorine a moment ago. Of course, fluorine would be a halogen located in this column of the periodic table, or this group of the periodic table. I would get to neon, and then what would happen after neon? I would then begin to populate the 3s. And so the element that would come next would have a 3s1 configuration. And maybe let's just write that out, right? So this is sodium. And so if we write the electron configuration of sodium, that's Na. We can see, of course, that it's got a 1s2, 2s2, 2p6, and then finally a 3s1. And notice what happened. Simultaneously, we ran out of states with the n equals 2 level, and we went to the n equals 3 level. And at that particular time, we went to the next row of the periodic table. These are directly related. So sodium has an S1 configuration, and we would expect sodium to behave exactly like lithium. And lo and behold, it's listed in the periodic table directly underneath it. It's true. These metals do behave remarkably similarly. And it's because of their electron configurations and because of all these states that are ordered the way they are, the periodic table is ordered the way it is. That's why neon comes before sodium, and that's why sodium has very different reactivity. Right? The structure of this periodic table matches exactly this orbital structure that we've discovered last class. We can continue on, and of course notice that after sodium, we can fill it up here, right? We can fill up and go to magnesium. And then, of course, after magnesium, we would have aluminum. But the point is that we could keep going through, and after the 3s, we, of course, have the 3p directly after. Not unlike the periodic table. In the periodic table, we had the 3s, and what comes after? There is nothing here in this range, in this gap here. We go directly to the 3p. And yes, there are 6 elements here described in the 3p row of the periodic table, or in that block, because there are 6 different combinations of electron configurations. Again, it matches. And once you're done, once you've gotten to that noble gas, argon, right here at the end, you then have the 4s. Okay, now notice this periodic table automatically accounts for that overlap that happens where the 4s gets inserted between the 3p and the 3d. It's automatically there. You get to the very next element in the row. This would be potassium. So potassium is our 4s1 element. There we go. So that's potassium. And once we get to potassium, it's going to behave exactly like sodium, or at least very similarly to sodium. And it's not going to have any 3d electrons in it whatsoever, but it shouldn't. We're just following the pattern of the periodic table. And once we get to the point where we've added 2 electrons. And so that would be the configuration of calcium there. And I can actually indicate calcium here if we want to keep track of these. So calcium, of course, has all of the same electrons that sodium would have had, but of course it would have 2 electrons in the 3s, but it would also have a full set of electrons in the 3p orbital, so that's 6 there, and calcium would of course have 4s2. So there we go. That's the electron configuration of calcium. And that brings us to this point in the periodic table where calcium is. So the periodic table is directly related to this orbital nature, orbital structure. And now I get to my 3D block, okay? And so the one part that potentially is confusing here is that the row of the periodic table had essentially correlated to the principal quantum number before. And generally speaking, that's true. This would be the first row, second row, third row, fourth row, etc. But the D block, what we call the D block here, begins with principal quantum number 3, okay, and that's again a consequence of this orbital structure. But the reason behind all this is evident based on the orbital model. We know that the 3D orbitals come after the 4s, and that's why we see elements listed here directly after the 4s. Why are there 10 elements here? There are 10 transition elements or D block elements here because there are 5 3D orbitals, which allows for 10 different electrons to be listed there, which allows for 10 different elements to have different properties correlated with having their last electron in the Ds. The structure of this periodic table is exactly matched by the orbital structure. And so even the fact that you could go and create a periodic table just by experimenting with how different elements behave, the periodic table itself is telling you that an orbital model exists. These are intimately related. And so as I go and I envision the electron configuration for all of these different elements in the transition block or the D block, I simply fill up my Ds over here in terms of their electron configuration. So for example, let's consider zinc. Zinc would be the last one here, right? And so if I fill all those in, we can see that I would have a D10 system. So 3D10, there we go. And so my electron configuration for zinc, if I were to write that out, of course, would be zinc 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Notice that I've taken care to write out my orbitals in their energetic ordering here. You will find differences between different textbooks and different sources that will choose to write this by principal quantum number. For example, so potentially you might find the 3D located here, but I generally stick to writing them in their energetic ordering, which is as you've seen here. And so there you go. There's electron configurations. There is the match between this orbital model and the periodic table. And therefore, my hope would be that you'll never get confused about whether the 4s comes before the 3D, because the periodic table itself is its own built-in cheat sheet to tell you about all the different orbitals and where they fall in the periodic table. And of course, you also have the F block. So these are the lanthanides and the actinides that maybe you're familiar with. And if you look through here and you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 elements. Why are there 14 lanthanides and actinides? Because as we add another set of orbitals, remember the pattern. We always add an odd set of orbitals. So we started with 1, we added 3, then we added 5, we would add 7 in the next case. So by the time we got to the 4, it would be 4F, and there'd be 7 of those. 7 orbitals can handle 7 times 2 or 14 electrons, and that would be able to describe 14 different elements, each with a slightly different electron configuration. So the very structure of the periodic table, why there is a pillar here that is 2 elements wide is because s orbitals can contain 2 electrons. Why there is a block here that is 6 elements wide is because p orbitals can contain 6 electrons. Why is there a block here that is 10 elements wide? It's because the d orbitals can contain 10 different electrons. And every time you add a new electron to this diagram, we're envisioning a new neutral element with another proton. And that is a unique thing, right? Elements are labeled by protons. And so we're literally looking at new elements every single time, and their behaviors, their chemical behaviors, would be dictated by how their electrons are distributed. Therefore, every time you add a new one, you have a slightly different chemical behavior. And if you list chemical behaviors that are similar in columns, for example, the halogens or the noble gases, for example, you will discover that the reason they behave similarly is because their last electron that you added is in the same state as the one before it, right? So the hydrogen atom has a 1s1 configuration, right? The lithium atom has a 2s1 configuration. And you keep going down, the sodium atom has a 3s1 configuration. And yes, there are other electrons, but it's always those last electrons that you add. These last electrons that you add have a special name. They're called the valence electrons, those outermost electrons in the largest orbitals, the highest principal quantum number electrons that you have. Those outermost electrons are known as your valence electrons. And those are the electrons that are going to be doing the chemistry. As two atoms come into contact with one another, it is exactly those outermost electrons that are going to be the ones that interact with each other and either create bonds or not, or do whatever it is that those elements will do when they come into contact. So the chemistry, largely speaking, is dictated by those outermost valence electrons. And so that's why we see reactivity patterns between elements that are in the same column of the periodic table. It's because they have the same outer electron configuration. All right, so we've talked about electron configurations so far. We've talked about how they exactly match the periodic table. And so this ordering should never be confusing to you. And also, we've come full circle from that original pattern I started discussing a couple of lectures ago. 1 orbital in the n equals 1 state, 4 in the n equals 2 state, 9 in the n equals 3 state. And then you add 3, and then you add 5, and this pattern keeps repeating, and it's exactly that pattern that produces the periodic table in the exact shape that it's in. Chemistry is essentially universally determined by that relatively simple pattern. It's amazing. These are inanimate objects, charged particles orbiting around each other due to Coulombic forces. And, the more you put together, these more intricate patterns get built until you get all of the chemistry of the universe. It's really an incredible thing. Okay, I want to talk about electron configurations in just a bit more detail. There are some more tricky cases, I guess, some things that maybe will behave anomalously in ways that you might not expect right now. So let's think about that. The first thing I want to do is I want to introduce the concept of a condensed electron configuration. So a condensed electron configuration is really just a way for us to write out all of this stuff, whatever the electron configuration has to be, in a way that's a little bit more condensed. That's where the name comes from. So let's take a look at the electron configuration of zinc here, right? So zinc is located right here in the periodic table, and it's what we call a D10 metal for reasons that I think are obvious. It's got 10 d electrons in its valence set, but potentially we would want to write this in a way that's a little bit more condensed, a little bit more convenient, because as I said before, and this is true, most of the chemistry is really happening on the outermost electrons. Okay, so let's think about how we might capture that. The way we do that is for any particular element that we wish to write a condensed electron configuration for, we locate it on the periodic table, and then what we do is we locate the noble gas above it. Okay, so the row above it would be this row, this third row of the periodic table, and the noble gas is always the last one on the right, of course. So for the case of zinc, this particular noble gas is argon. And although our periodic table doesn't explicitly indicate that, let me just point that out here, that argon is that particular noble gas. And so we use this to our advantage by writing a condensed electron configuration as follows. We would say that zinc has all of the same electron configuration as argon does, and so we indicate that in square brackets there. Plus some other stuff. Okay, so we know that after we get to the argon position of the periodic table, we've got more electrons to account for before we ultimately get to zinc. But what we can do is we can prevent ourselves from having to write essentially all of this information here just by indicating that we have the same configuration as argon, plus some other stuff. And so what is that other stuff? I think that's obvious. It is 4s2 3d10. So this is what we would consider to be the condensed electron configuration of zinc. And it's a little bit more convenient to write and still captures all of the valence electrons. In fact, this is what we could define as valence electrons. Core electrons could be all of those things encapsulated within the row previous to the element we're talking about, right? So all of this stuff in green we could call the core electrons for zinc. And anything we write afterwards we could consider to be the valence. And so these words core and valence can be adequately described that way. Now, the next thing I want to talk about is I want to use this notion of the condensed electron configuration just to help make it a little bit more convenient for me to talk about what might appear to be some anomalies in electron configurations. Very common anomalies, things that are talked about quite often in a first-year chemistry class. And let's take our zinc and realize, of course, that that's corresponding to 4s2 3d10. However, let's just detour for a moment and let's talk about copper. Okay, I want to talk about copper. So copper is located right here in the periodic table. And so your, I think, intuitive electron configuration for copper, the thing that you would probably write is you would notice that it goes to the 9th position in the D block, and you would probably write, and let's actually just edit this particular one, you would probably write for copper, you would say the copper electron configuration is argon 4s2 3d9. My guess is that that is how you would write it. And if we had to draw an electron configuration in the orbital energy level diagram, we would just omit one of the electrons from that part of the diagram. And so we'd have 9 electrons in the D block up here, and everything else would be the same, and this would be the resultant configuration. And unfortunately, I'm here today to tell you that this isn't correct. Now, there is good reason for this not being correct, and we can talk about that and explain it in some detail. But the first thing we've got to realize is that this isn't exactly the correct electron configuration for copper, at least not neutral copper in its ground state. So really the question is what's going on here? Why is this different? We could think of it this way. I removed an electron from zinc, and I had chosen to remove this particular electron right here. And so if I'm being told that this is wrong, and perhaps we should be explicit about that, and so let me just sort of indicate that here. If I'm being told that that's wrong, what is it that's so wrong about it? Well, the first way that I would attempt to explain this to you is I would want you to remember that the energetic positions of all of these orbitals are, of course, always fluctuating, right? Every time I add a new electron to this diagram, all of the orbitals, their energies are all modified somewhat. They all adjust. Every time I add a new proton to the atom I'm talking about, in other words, change its identity to a different atom, another proton, will exert more force to all of the electrons, and so all of these electrons will be drawn presumably tighter to that nucleus, and it will therefore be, happier from an energetic perspective. And so the energies of all these orbitals adjust for that. And this is something that we lose, I think, when we look at these static images in a textbook, or even on this slide that you're looking at right now. We start to believe that these orbitals are in fact static. We start to think that the 3p orbital is always at that energy. But don't forget that, for the hydrogen atom, all three of these n equals 3 level orbitals, the set of d's, the set of p's, the s, they were all there, but recall that they were all at the exact same energy, right? And it was only when we went to helium and then, elements further along down the periodic table that these orbitals started to stratify. They started to separate from one another. And we talked about why that was when we discussed that stratification. It's that you have competing effects. You've got more protons as you go down the periodic table, which exert more force on these electrons, which make the s orbitals happier than the p's, and the p's happier than the d's, so on and so forth, so that these s orbitals can be pulled lower in energy. And of course, the p orbitals are pulled lower in energy too, but not by as much. And the d orbitals are pulled lower in energy too, but not by as much, so on and so forth. And this was ultimately what led to this ordering shift in the first place. But let's remember that the 3D and the 4S are actually incredibly close in energy anyway. And what does that mean? What's the result of that? It means that if we make subtle modifications and, say, stabilize the set of 3D orbitals in some way, it's possible that this set of 3Ds can actually be stabilized further than the 4S. This is a possible change that can happen. And what really dictates whether or not that change will happen is the orbital occupation. So how many electrons and what kind of electrons we put in all of these places. That's an important thing to realize. Okay, so while you would expect, of course, that the 4s orbital, generally speaking, was less or lower in energy than 3d orbital, that isn't wrong, but it also isn't etched in stone. And I think that's the most important thing to realize here. Yes, we think of the 4s orbital as being lower in energy than the 3d orbital, but it's not etched in stone. We can do things to change that, simply because they are so close anyway. They're very, very close. This is different, say, than if I were to, say, significantly stabilize the set of p's, for example. So suppose I could do something, and we can actually talk about this in a future lecture, but suppose I could do something to impart some sort of special stability onto this set of p orbitals. And suppose what I did to impart stability on these p orbitals didn't impart stability on this 2s. You might ask, is it possible to bring this 2p orbital below the 2s orbital? And my answer to that would be no, not because it's a physical impossibility, but because the gap between the 2p and the 2s orbital is so big that it would be virtually and practically impossible to do something to the 2p orbitals to make them so much more stable. There's just too much of an energy gap to overtake. And that energy gap is difficult to indicate on this static image. And that's one thing I want you to appreciate. We're not necessarily indicating the energetic scale here to the left. Some of these orbitals, so for example, the difference between the 1s and the 2s is actually enormous. It's not well represented by this image. But the difference between the 4s and the 3d is, quite frankly, very small. And that's why making some edits to the set of 3d orbitals that would somehow stabilize it is sometimes enough to bring it below the 4s. And sometimes enough to make it the more stable place. Okay, and copper is one of the earliest examples that we can use to highlight this and bring it to light. So the question was, really, if we pulled the electron out of here, was that the right decision? And we've discovered since that seems to not be the decision. But I would argue that really the only other thing we could have done is, let's say, removed this electron. So I just took that one out of the 4s. and suppose we placed it up into the 3D. So take a look at this particular configuration. The one I had just had previous to this was, of course, the one that I indicated was wrong. 2 electrons in the 4s, 9 electrons, or sorry, 9 electrons in the 3D. What I've indicated now by shifting that electron would be the following. It would be copper as represented by the electron configuration of argon, and then a single 4s electron and 10 3D electrons. That is the configuration that I've now got drawn over here, okay? And it turns out that this is actually the correct answer in this case. And the reason is, again, because of this orbital energy level switch that can happen. It turns out, and I will show you evidence for this in a future lecture, but it turns out that having a set of orbitals that are, for lack of a better word, identical. And so let me be clear here. Identical meaning 2 electrons in every single one. Okay, I've filled this set of orbitals. Filling the set of 3D orbitals does actually impart some special stability to it. It is a more stable state to have a set of orbitals filled than not to. Okay, so it is more stable to have this set of orbitals filled than to not to. And of course, in this first case, in our first guess, we didn't have the full set filled. We had one vacancy over here at the end. Now, you could say the same thing. You could say, well, hold on, if it's so special to have orbitals filled, then wouldn't it be better to have the 4s filled than not filled? And the answer to that is yes. It is true that a 4s orbital would generally, relative to the other orbitals, it would be more stable to have it filled than not filled. And again, I haven't shown you evidence for this, but I will. But we now have a balance. We have a decision to make. Is it better to make the 4s especially stable with a full set of electrons inside, or is it better to make the 3D especially stable with a full set of electrons within it? And the correct answer is, of course, that it's better to make the 3D set full for essentially 2 reasons. One is, recall that the 3D and the 4s are so close in energy anyway, any subtle change in either direction can, in fact, cause the 3D to overtake the 4s and become lower. And putting all 10 electrons and filling the complete set of 3D orbitals turns out to be enough to do that. And it is better to create a full set of 5 full orbitals than it is to create just one set of 1 full orbital. So there's just more benefit to this. Is there an energetic cost? Is there a penalty, if you will, to removing the electron here and placing it here? Of course there is. And in science in general, there's always a balance between energetic costs and energetic benefits. And I'm simply saying that the cost of removing the electron from the 4s orbital is outweighed by the benefit of having this full set of 3Ds. So that's the moral of the story here. And this is our final correct electron configuration for the carbon atom. Okay, and so how we arrive at this is we notice that at the the D9 spot here, and so we would expect other elements to behave the same way. When I've got this scenario where I've got 2 orbitals that are really close together, because there are so many Ds, the energetic benefit of causing them all to be full will cause a lowering of these 3D orbital energies. And it will be overall better because the 3D can actually come below the 4s in this context. And so it would be overall better to do this from an energetic perspective. Now, when we go beyond copper to, say, nickel, so let's highlight where nickel is in the periodic table. So nickel happens to be right here. The electron configuration for nickel does not adhere to this principle, right? So the electron configuration of nickel has argon in the same as what we saw before, and its electron configuration for neutral nickel does actually have 4s2 3d8. Okay, now that's the intuitive one. That's the one you might have expected for nickel prior to this discussion of this reordering of orbitals and energy states. Now the reason is, and if we do this, let's actually talk about nickel over here in our diagram. So let's remove another electron because nickel has one less electron than copper. In this particular state, well, we've got a few things to do. It's better to keep our electron with the 4s2, and let's actually remove this one here. Okay, so this would be our 4s2 3d8 state. Now let's take a look at this. A common question that students would have is, if it's so good to fill the 3d set, can I take one of these electrons and place it here, and one of these other electrons and theoretically spin flip it and place it here, such that I have a full set of Ds and none in the 4s? And I can confirm to you that filling the 3Ds would be a good idea from the perspective of the 3Ds, but it would cost us to have to remove both electrons from the 4s, right? And there's an energetic penalty to that, right? There was a penalty to taking that first one, right? There was a cost of doing that, but it was worth it because we ended up being able to fill the Ds. Taking the second one has further cost to it. And what I'm here to tell you is that the energetic benefit of filling the Ds, which is essentially the same energetic benefit as before, is not enough to be worth it to take 2 electrons from the 4s. Only that first electron turns out to be worth it. And so really copper, and more specifically this D9 position in the periodic table, is really in that special place where it turns out to be worth it to rob an electron from the 4s in order to fill the 3d set. But it's not worth it to do it twice. And so nickel brings us right back to what you might call normal, or the intuitive way of doing electron configurations. Now that doesn't mean we're finished with anomalies. In fact, we can continue along this path and consider something like, say, element number 24. Let's talk about chromium. Chromium would be located here on the periodic table, okay? Now the intuitive electron configuration for chromium, what you might think, would again be all of the same stuff that argon has, but now potentially 4s2, we would think, and then potentially also 3d4. That's, I think, what we would expect, right? 1, 2 in the 4s, and then 1, 2, 3, 4 before we get to chromium. So this might be the intuitive electron configuration that we would expect for chromium. So let's adjust our diagram up here so that it matches that, 4s2, 3d4, and we have a look and we go 1, 2, 3, 4. It's our high spin state. That should be what we'd want. Okay, and now the question is this the right electron configuration for chromium? Let's recall some of those anomalous rules that we were thinking of before. By the way, the rules aren't anomalous. It is always true that a full set of orbitals, or a set of orbitals that match symmetrically, right, half full, does impart some added stability. It's a good thing to do. The question is it good enough relative to the cost that you would have to impart on the system? Okay, so what am I talking about? How does this relate to here? My question is, take a look. We've got 4 d orbitals, and then one of these things is not like the other. This is very similar to the scenario we had with copper. The first 4 were fully filled, and then we had a half-filled 5th. In this case, we've got a similar situation. We've got 4 that are half-filled, in other words, look the same, and we've got a 5th that is standing out in this particular scenario. So the question that I would have for you is, first of all, is it true that a full set of orbitals where all of them had the same number of electrons in it, is that a stable thing? Is that an especially stable thing to do? Would it be a good idea to do that? And again, it is true. That is a stable thing to do, and I'll show you evidence for that in a subsequent class. So it is a good thing to do to fill this, or at least half fill this last orbital. The question then that we'd have to answer is it worth it to take one of those electrons from the 4s and place it there? Is that something that's worth it to do? And I suppose technically speaking, to keep a high spin state, I should indicate my remaining 4s electron that way. So the question is that the right thing to do? That's an alternative, and it's an alternative reminiscent of this copper anomaly that we were just talking about. And the alternative would look like this. I would again keep my argon configuration, and I would have a 4s1 3d5 configuration. And so which is it? I can certainly tell you that this is a good thing to do for the Ds, but a bad thing to do for the 4s. And like always, the question we need to think about and answer is it worth it? Is it worth it doing this bad thing to the 4s to do a good thing to the 3d? And the answer is yes. Again, just like in the case of copper, my correct answer here is this anomalous, or at least seemingly anomalous option, where I take an electron from the 4s and I place it into the 3d. Now my answer here is really again for the same reason as before. Remember that this 3d and 4s set of orbitals are so close in energy that subtle little changes can be important. And although it costs energy to remove the electron from the 4s, essentially rising its energy, it's a good thing to do to the 3d, and the 3d can come down. And overall, there's a net benefit there. It is a net positive effect. Or I should say a net negative effect on the energy. The energy goes down, and this is a more stable configuration than what we had previously. And like I always stress in this class, matter wants to be stable, and so it will tend to adopt the more stable configuration. So we've got this special scenario in the D9 column of the periodic table, as well as the D4 column of the periodic table, where we can rob an electron from the previous S and help us either create a fully half-filled set of Ds, as I have here, or a fully filled set of Ds, as I did for copper. And so look out for scenarios like this. It's not just chromium, you've also got molybdenum below it. And it's not just copper, you've also got silver below it. Okay, and so these elements, these what we call S2D9 elements, really should be S1D10 elements. And the S2D4s really should be S1D5s. And again, as I go further here, so beyond chromium over to vanadium, that would be right here, that's an example kind of like nickel, in which case we really can't take 2 electrons from the 4s. That would come with too significant of an energetic penalty. And so we won't be doing that, and that's not the correct configuration. The correct configuration is the intuitive one, the one that we would have arrived at anyway. So with that, you know all about electron configurations. The only real edits to this would be if we had ionic species, for example. So suppose we had some elements that had a charge to them. And so we can think about that, for example. If we had a charge, so imagine, let's think of a commonly charged species. Imagine fluorine, but fluorine as a negatively charged species, so an anion. Really the only edit that we have to make to this is realizing that the fluorine anion has an extra electron. So if we know that fluorine is typically present here in the periodic table, then we know that it's, generally speaking, a 2p5 element. And I could write its condensed electron configuration as helium, because the helium atom is the noble gas above it. And we would say 2s2, and we would say 2p5 for neutral fluorine. But given the fact that we've got an anionic species, we've got an extra electron. And so what we do is we imagine it to have the configuration of whatever element is next to it, that extra electron. So it would be what we would call isoelectronic with neon, which is the element in that position of the periodic table. And so we'd have to add an extra electron to this to take that into account. And so this would be how you would do the electron configuration of a charged, or in this case, anionic species. Likewise, if you had a positively charged element, so let's think of something like potentially magnesium. These are things that generally have a positive charge. What about magnesium 2+? Okay, so where magnesium generally is in the periodic table is its element 12, and it's generally has a 3s2 configuration. So it would be right here in the periodic table. But in this particular case, we've removed 2 electrons. It's magnesium 2+. So what I would want to do is then take an electron away, and we would say it would be isoelectronic with sodium, which would be right here. But then we would take another electron away, and it would again be isoelectronic with neon, right? Similarly to the fluorine species here. So if I wanted to indicate its electron configuration, of course it would have the helium configuration, but it would also have the 2s2 and 2p6 configuration. So really doing electron configurations for charged species isn't really all that different than doing electron configurations for neutral species. You really just have to keep into account the fact that the electron number changes, and if the electron number changes, you just add or remove electrons accordingly. And so that's really it. And so now we have all of the information we need to really tie together the many, many different energetic states that our electrons can be in for all of the elements of the periodic table. And we know that all of those orbitals are exactly what predicts the shape of the periodic table and its structure. And why is there a block of 10 elements here? Why is there a block of 6 elements here? That is exactly because of this orbital structure. They're intimately related. And with all of these different electronic energy states comes so many different options for electrons to be excited and then relax back down, which gives you all of the different barcodes, all of those different patterns of emission lines that can be released by the different elements of the periodic table, which, because of where these orbitals are completely unique to each one of these elements. And that's why we can use spectroscopy and light to tell us precisely which elements we have in a system based on their unique barcodes that'll be emitted regardless of what molecule that element came from. It's an incredibly powerful technique, and it's completely characteristic. And what we'll do in our subsequent class is talk about how we can take these electron configurations that we now know so well and actually predict the properties of these elements. Which elements would make good batteries? Which elements would make terrible battery materials? Which elements would bond well with their neighbors and which wouldn't? Which neighbors should we choose to make great bonds? All of this comes out of fundamentally electron configurations. So stay tuned.